The dissertation topic I've chosen is modeling uncertainty and burn severity using a composite burn index and remotely sensed data. And I hope by the end of this, you can really read that title in a different way and kind of chew on it and understand some of the components and concepts that are included in that. So let's just start out by talking about what burn severity is in general. And there's really a whole infinite number of ways that you could measure burn severity. When we say that word, we're really just talking about some degree of change between a pre-fire and a post-fire environment, or what were the effects of fire on the environment. And this is often used for management contexts in terms of prioritizing where you might do remediation or treatments in a post-fire landscape, meaning you might want to do different types of work in a high severity area versus a low severity area. And it's also used in a lot of research applications to track and monitor changes in fire regimes across time and across space. But what are we really moderate and high? And we'll get to that in just a moment. But in this context, I just want to introduce a few ways that we could measure severity itself. So in this landscape, you might be interested in looking at are the large trees surviving on the landscape that might serve as seed sources for areas where you had young trees die. You might also be interested in looking down at the soils and saying, hey, what's going on with the litter and organic matter that's stored in that? And is that posing a threat to waterways, or is there erosion that may contribute to water quality issues? Maybe you're a carbon researcher and you're interested in carbon sequestration, and you're really interested in tree mortality and understanding the dynamics and impact of that on the ability of ecosystems to store carbon. Or you're looking at treatment effectiveness of fuel treatments across a landscape, and you're looking at an area where you treated beforehand, and you want to know what are the general effects of that area, and was the treatment successful? So without reading through this table, what we recognize is there's a whole ton of ways that studies have modeled or measured burn severity in the field. And my focus kind of from a forestry standpoint is really, hey, what's going on with the soils? Maybe we want to look up and say, what's going on with the trees? Or really what I ended up in this dissertation was this last topic here, composite indices. And that's really a way to kind of combine attributes across the entire ecosystem from the substrate and soil strata up through the canopy to the big trees, and kind of say, what's the general effect of the fire across the entire ecosystem? This dissertation is really focused on this composite burn index, which is just a protocol of how to measure and assess these attributes in the field. And what you can see just through this list is that you're looking at 5 different substrates or 5 different strata, from substrate, herbs, shrubs, up to intermediate and tall trees. And then there's a number of categories of things that you assess within those. And this protocol visually or qualitatively looks at each of these ecosystem characteristics and ranks them according to how much change occurred on the landscape. And often we see these grouped together in a way. So if you group them all together, we call that overall plot severity. And then people also group just understory versus overstory strata together and look at the differences there. Now we'll come back to that later. And then I just want to highlight one kind of key change or update that occurred in this protocol, which is called the geometrically structured composite burn index. And this takes into account the fraction of cover of these strata. And so you're not equally weighting all of these when you average them together. You're taking into account how much cover each of these strata is, and it's sort of a weighted average. And then also takes into account leaf area index change. And so those are some updates that try to make it more representative of the true ecosystem change and more related to what is being measured by remotely sensed data. What are some benefits of this type of composite index? It's very, can be employed rapidly and quickly across large landscapes, and across these massive fires that we're seeing these days. We really don't have the time and resources to go and sample everywhere on the landscape. And so we need a quick and dirty method to go out and get a general sense of what's happening. Also, you may be working with people that don't have a very specific or targeted application for what they want to understand severity. They just want a general metric that they can use. And so this kind of satisfies that criteria. As you think about the consequences of averaging these different characteristics into one metric, you do lose some of the inherent kind of connection to the ecological phenomena that are occurring on the ground. And so this is really, hey, that's a critique, but if you're really not sure what people are going to be using this for, then a general composite metric does make sense. And it's nice for kind of a general comparisons of things across space and time. And so we can aggregate these measurements and compare different fire effects in a general sense. We've seen extensive work in the literature that compare this composite burn index with remotely sensed data, and very robust or generally robust relationships with spectral fire severity indices. And we'll get into exactly what those are in a bit. And so when we do this field observations of remote sensing, often we're sampling in a few places or a number of places on the ground, but we want to measure severity wall to wall across the fire. And that's where remotely sensed data comes in. And why is remotely sensed data so powerful in this context? Well, there's a few bands that really stand out as responding strongly to fire. And the first one I want to call out is this near infrared band. And if we look at this graph, what we see is this line for green vegetation often is reducing after fire. The reflectance in the near infrared band experiences reductions or decreases because of the loss of green vegetation on the landscape. Similarly, the other band that we'll visit numerous times throughout this discussion is a shortwave infrared band. And this is responding strongly to increases in char and reductions in moisture across the landscape. And so I don't want to go through all of these, but there's been a ton of literature that has kind of accumulated conceptual theory about how and why these bands respond to fire. And again, the near infrared and the shortwave infrared is really going to be underpinning this entire dissertation. And I want to call out again the consumption or damage of leaves, and then the exposure of ash and bare soil and charred logs as kind of driving the responses in those two bands. The outline of the actual work that I did that goes into this is going to be the 3 chapters that I have to present, different approaches. Well, let me just kind of give the context of these 3 chapters. The first one is a methodological review of all of the ways that composite burn index has been modeled and linked to remotely sensed data. And we found that the key result there was really that all of the methodological differences between studies can make it challenging to compare results across different fires or studies where the researchers and authors took different approaches to modeling the composite burn index. And then we took a deep dive in the spatial and temporal alignment between field observations and remotely sensed data. And this chapter really allowed us to leverage the data sets and the studies that we had aggregated throughout that review process for chapter 1, and then start to analyze and process the data just to get at these spatial and temporal concepts a little bit deeper. And then we underwent a very extensive model sensitivity analysis using the King Fire as a case study. The kind of some permeating concepts you'll hear throughout this are really number of things that popped up throughout every chapter are uncertainty, accuracy of measurements and models, sensitivity or precision, And then what are these being applied in the context, and how comparable across different fires or different studies are results. So why did I undertake this study? Well, I really got interested in this topic and I started reading all of these papers. And what I found throughout all of my reading was that, well, number one, there was no one place where you could go to understand the whole field of the science and what was going on. And number two, every study you read was using a different approach. And I was really curious about spelling out all of those approaches and trying to understand how influential those methodological differences might be, and how burn severity in the CBI context can be interpreted. And so let's dive into chapter 1. This is the methodological review of the Composite Burn Index, which really means doing a systematic literature survey, extracting all of the methods and processes that CBI, and then creating kind of a construct of a framework and spelling out the decisions and starting to dig into how comparable things might be. And so really basic study questions kind of stepped us off on this process. Where and when have the studies been conducted? How is burn severity measured in the field? How is burn severity measured from satellites? And then how are those field observations and satellite imagery modeled together? The goals, what we were able to accomplish with this chapter was get a big picture of the state of the science. What's been done? How is it being done? What are the important decisions in this analytical process that are being done? And what are some key gaps in research to date in the Composite Burn Index context? And then from there, we were able to suggest some criteria for making methodological decisions. And I will also say kind of call create a call to hope for studies to report things in a more consistent manner as a part of that as well. So I think if I had to sum up, this in an elevator pitch between 1 and 2 floors, I'd say, hey, there's a lot of ways this has been done, and there's not enough comparative studies. And what does that produce? It produces a lot of uncertainty. It means when managers or researchers are trying to interpret 2 studies that use different methodological approaches to model CBI, they really have to weigh how much the difference in those results is reflective of the different methods that were used versus the ecological phenomena that they're likely more interested in. Can they compare those studies directly, or are the differences in methods so are driving so much variability and uncertainty that they can't clearly interpret the ecological phenomena that they want to? So underwent this systematic search, basically set out a list of key terms to search through a number of databases for all of the papers that had done this work. I should highlight here briefly that I was really focused on Composite Burn Index as a continuous variable. There's a whole suite of studies that also model it as a categorical or a classified variable. Those 2 approaches have different, they're valuable in different ways. And there had been a lot of work done to synthesize literature on the classified approach. And so the continuous use of CBI was really where the focus of the study was. So I went through this whole literature search, aggregated all of the studies that I found from those 3 databases, read all of them at least far enough to determine if they would be included or not, meaning they had empirically measured CBI on the ground, and they had created models to link that to remotely sensed data. And so there was a lot of studies that just didn't meet those 2 criteria. And the third, I guess, being that that the models were modeling CBI as a continuous variable. And overall, I found these 62 studies. While that number may not sound extreme, it was quite a few papers to read through and create this whole rubric of information that I extracted from them to do. This process, basically, you can imagine at a high level, detailing the framework of what was going on in these processes. So how is field data collected? What decisions are made there? How is remote remotely sensed data being collected? What are the different types of data sets, different spectral indices that are being calculated? How is that happening? And then how is the modeling itself occurring? And so I'm going to try to be brief walking through this, this study. There's a ton of results that we have compiled, and this paper is in submission right now. And so I really encourage, if you're interested in this, to either come talk to me or wait a month for the dissertation to land in the library and then read it there, or however long the review process takes. But the key point here is that we really went in depth, splitting out all of these different decisions and the options within each decision that studies had done. This is a map for the field data, and then the remotely sensed data, and then the modeling that was done. And you can imagine, as you start to look at, really can get very, very big, the number of pathways you can take to actually collecting data and then to getting a model out of the back end of that data. And I just want to highlight like some of the results we're able to kind of aggregate and show here. This is a table of all of the satellite and remotely sensed data that had been used in any study that did this process. So we're able to see on the right the number of studies that used these types of data. By far and away, Landsat satellite imagery is the most commonly used. And then we see a variety of different spectral, spatial, and temporal resolutions arising as well. And so this just kind of tells us, where do we have strong confidence in remotely sensed data and the ability to do this? Or where is there still need for more work to be done to understand how novel data sets can be used to model CBI? So as we look through that and just think about this in the context of remotely sensed data, we're able to split out how many studies used optical imagery versus radar, thermal, or mixed, basically a combination of optical and other remotely sensed data. Of those, how many use just a single post-fire image or data set versus a pre and a post-fire image versus other kind of relativized or other types of indices. And I'm not going to go in depth to these indices right now. I just want to highlight in this here that remember we talked about the near infrared and this shortwave infrared bands being really important. Those comprise one kind of very, very well studied index called the normalized burn ratio. And we see that showing up in the vast, vast majority of papers that have modeled CBI. And then there's this other piece I'll just highlight, this DNBR offset. And this is used only in cases where you have pre and post-fire imagery. Often it's recommended that studies look at the difference between pre and post-fire reflectance in areas that did not burn. So outside the burn, areas where you expect things to be relatively stable, you're still experiencing differences in reflectance due to things like phenology, sun angle, solar zenith angle, or other things. And so really this is a correction for the reflectance in areas you expected to be stable. And surprisingly, we see not a ton of studies have actually included that in their analysis. But that was one thing I was kind of curious about. So what are the key decisions? Really quickly, just running through them, and you'll see these kind of pop up in the third paper, types of field data that have been used and modifications to those protocols, data selection, what satellites, how many images, pre and post fire, the timing of those images, what are the spectral indices that you're actually calculating. I'm really focused on near infrared and shortwave infrared, but there's there's different bands ranging from just the visible wavelengths to non-visible wavelengths and hyperspectral imagery that includes many bands as well. Did studies do georeferencing or co-registration between image pairs? how did they get the pixel value to associate with the plot itself? What model forms were used? What performance metrics were used? And did they break things down by strata? And what I really am just listing these out for is I want to highlight the number of these that we really were able to tackle in that sensitivity analysis in chapter 3. And so the key takeaways here really, again, there's a wide range of approaches that have been done, and there's a lack of consensus on the quote unquote right way, which, throughout this, I think you'll find my conclusion at the end being that there is no right way to do this. I think there's some suggested approaches that are reasonable to consider, but the application, it's very application dependent. There's not a ton of studies that have compared options at any one point in the decision menu. And of the ones that had, for every conceptual rule of thumb, there was an exception. And so one example I'll bring up here is that a lot of studies think that the overstory canopy will be better predicted than the understory based off passive remotely sensed imagery. So when you take a picture from a satellite looking down, the image there doesn't penetrate the forest canopy. It's just the field of view, what you can see. And most of what you can see is the tops of trees. And so this rule of thumb suggests like, hey, we can better predict change in overstory canopy than we can understory canopy. But in the literature, I found that that was still mixed results. Some actually perform better in the understory than the overstory. And that type of rule of thumb exception occurred throughout almost every comparative study I could find. And then there's an absence of this comprehensive kind of beginning to end quantitative analysis. And then we also identified some key research gaps, but I think this comprehensive beginning to end analysis is what really struck me as a potential point for contribution in chapter 3. Some of the recommendations we're able to make here were really spelling out all of the key decisions. And I think asking future researchers to be more explicit about why they're choosing one reason versus another. And so in that paper, we provide a whole suite of rationale that could be kind of used to explain why you went with one option versus another. And model selection is a key example here where we identified throughout the studies that had occurred, this had kind of came out through those studies that a number of them are doing model selection just based on a performance metric like R squared or root mean square error. And there's also a kind of a tension between that and picking models that are better representative of the ecological phenomena that you're trying to model. And so we'll look at some of those issues again in chapter 3. And then again, we called for kind of key elements or suggested that key elements be reported, where as I was going through this literature review, I ended up having to contact a number of authors to say, hey, what was the timing of your field data collection? Did you include this DNBR offset or not? And so it really gave us, hey, from all of the information I wanted to extract, here's what I would like for future studies to more explicitly report. Chapter 2, I'm going to try to keep chapter 2 as brief as I can here because I really want to dive into chapter 3 with everyone. And so chapter 2 was using those studies that we aggregated from chapter 1, some of the information that we extracted in terms of the spatial and temporal alignment between field observations and remotely sensed data. How well aligned are those, and what are some kind of first order principles that can inform potential choices or methods that are used? And so we asked, how or does the spatial alignment of plot and pixel grain drive variability, and how these spectral indices are extracted? And how temporally synchronous are field data and fire ignition, and then field data and remotely sensed data? So I think I'll first explain what is pixel value extract. You have a plot. In this case, the plot center is represented by this cross, and then the plot diameter by this circle. And people have both circle and square plots. So for the presentation, I'm just going to focus on circular plots We have analysis of square plots in the paper as well. But you could just look at where that plot center lies and take the pixel value that's directly overlaying that plot center. Okay, that's one approach you could use to associate the value of the spectral index that's from the remotely sensed data with the plot that you've measured severity on the ground with. I hope everyone can kind of see, and it may be a little difficult here, that these are pixels, and there's a this is a 3x3 window with 9 pixels. So varying shades of green up here are kind of separating these pixels. You could also take a focal mean. So if you just look at the pixel that overlaps the plot center and then draw a 3x3 window around that, you could calculate the average of all of the pixel values that fell within that 3x3 window and associate that with the plot. Bilinear interpolation looks at the closest 4 pixels, and then it weights their average value by the distance to those 4 pixels from the plot center. And then area weighted average would look at whatever pixels that plot overlapped, it would calculate the area of the overlap and then weight the average pixel values by that area of overlap or the proportion of overlap. And then another interesting approach was just to place random sample points within your plot. And in this case, I've placed just 5 random sample points and then take the average of the pixels. Basically, let me explain it like this. It's like the first one where you just take the pixel value that overlays the plot center, but now you take that for each of the 5 points surrounding or interspersed within that plot, and you average those 5 values together. There's a few others we included in chapter 3, but I just want to kind of run through some examples of what those are here. And what we ended up really thinking about was this concept of pixel versus plot homogeneity. And so you can imagine if you try to align a circular plot with a square pixel, there's really 2 ways you could align it and kind of be quote unquote like right or like matched up as best as you can. You could align your plot so that it's nested just within that square pixel, or you could not align it, but you could define a plot size such that if the plot exactly overlapped a pixel, the diameter of the plot would fall within that pixel. I'll talk about it in a moment. It's virtually impossible. We never actually try to draw the plots on the ground exactly within a pixel, but this is just in terms of defining the size of those plots. Or you could define the size of the plot so that it's surrounding the square. And anything within that, for the sake of this chapter, I just called spatially aligned. And then if you're outside of that, there's 2 cases you could have where the plot is much smaller than the pixel, or the plot is much bigger than the pixel. And so if the plot is much smaller than it, you can think your assumption by using the remotely sensed data with this pixel is that the landscape captured by that pixel is relatively homogeneous, because the imagery collects this synoptic image that aggregates all of the objects within that pixel together into a single value. And so the idea here is saying that you're assuming pixel homogeneity would be really, it wouldn't matter if you shifted your plot slightly around within this circle, the value of that plot is really going to stay the same. The pixel, or the value of the pixel is going to stay the same. The plot, as you're shifting it, may change, right? Because you're moving on the ground within that area. And so the best assumption to consider here is that pixel is homogeneous. It doesn't matter exactly where the plot falls within that pixel area. Whatever value you're going to sample for that plot ought to be relatively similar. On the flip side, plot homogeneity means that if you just looked at 1 pixel here, you would kind of assume that regardless of where that pixel was within the plot, it wouldn't change much. And so the plot should represent an area of like kind of similar severity. However, I'll emphasize again how the sampling methods can help us overcome these assumptions. So the way we characterize these spatial mismatches is, hey, you have differently sized field plots relative to the size of the pixel in the remotely sensed data. There's geometric errors within both the plot GPS locations. So the GPS that you've used to extract the coordinate of the center of that plot has inherent error in it. And so you're unable to precisely locate that plot. And the pixel location itself has error from the satellite positioning. And so even if you are able to hypothetically match the pixel location with the plot itself, both of those could be slightly shifted around due to this error. But really what we're dealing with is this random error of the plot center relative to the pixel center. There's no way to actually align these spatially in the real world. And so we come back to these kind of sampling approaches and we think about how big is the neighborhood of values with those pixels that you're looking at to calculate that spectral index and associate it with the plot. Of course, here I've plotted a 30-meter diameter plot with a 30-meter by 30-meter pixel. But you have to imagine how these relationships might change if the plots were very big, for example, or very small relative to that pixel size. And so we come back to this kind of diagram, and on a graphical format of this, I was able to basically carve out an area of like what would be considered spatially synchronous or spatially aligned in a better word there. It would be anywhere where the plot was and pixel relationship fell between these two. And then in this case, you would have a pixel homogeneity, which puts you above the line, and then plot homogeneity, which puts you below the line. Actually, I'm explaining this a little bit too much now because I pulled that slide out just for the sake of time, and I wanted to just focus on a different summary of how we looked at this or assessed this, was using this assumption strength index, which really characterized from a positive to negative scale whether you were in that pixel homogeneity space or plot homogeneity space. And the first thing to recognize is that there were a lot of studies that actually matched the size of the grain of their plot to the remotely sensed data or pixel level. And then ones that fall in the positive realm of this assumption strength index mean that they were relying on this pixel homogeneity assumption. And so, hey, maybe it makes sense that a ton of those studies use means they just use the value of the pixel that directly fell over the plot center. And so maybe that makes sense because as you shift this plot around, you're really probably staying mostly in one pixel unless that plot falls very close to the edge of that pixel. On the flip side, we have the plot homogeneity assumption, which in this case, you could imagine it being more beneficial from a conceptual standpoint to sample a larger neighborhood of plots, or sorry, a larger neighborhood of pixels within that plot. And so, for example, the mean sample of points within a plot means you would scatter points all along this plot, and then you would take the pixel values and average those together where those points fell over. Or a focal mean, you could actually take a 3x3 mean of these pixels. And so some of those methods characterize larger neighborhoods or potentially characterize larger neighborhoods of plots of pixels. Sorry, pixels and plots are tongue twisting me right now. And I do just want to highlight here that a lot of studies didn't specify how they did this. And so really part of this is calling on some of those to be more explicit of their methods. Just really quick, we plotted some temporal synchronicity concepts too. This is looking at the timing of field plots relative to the timing of the start of the fire. And so obviously they all fall above the line here because all of the severity plots were measured after the fire. But the key here is really emphasizing that we know a ton, or we have a ton of information about what's happening in the first, say, 16 months after a fire, especially around 1 year post-fire, which probably corresponds to the kind of summer field campaigns after a fire has burned. And we lack a lot of information about longer term dynamics in terms of these models there. And if we look at the temporal synchronicity between the field plot timing and the remotely sensed timing, this means that when did you collect your field plots relative to acquiring that remotely sensed data? From a conceptual standpoint, it's encouraged that people time those as closely as together as possible. And so this kind of shows us what's the spread in this data. And ideally, a more in-depth analysis could start to understand how influential is this? Because these studies often use different methods, I've really relied on the subset that used multiple post-fire images at different date to assess this. And interestingly, I found, again, the rule of thumb was broken where sometimes remotely sensed data collected a year or multiple 2 years after the plot was collected was a better predictor of that plot level severity than imagery collected more synchronous with that plot. And so again, just these exceptions are arising throughout this work. Key takeaways from this chapter: many studies don't explicitly state how they actually got that spectral index out to associate with the plot or the timing of field plot collection. So the graphic I showed was really a subset of all of the studies for the ones which actually did report that information. Another thing that would be interesting to do here would be to collect field plots of nested size so that you could more accurately assess the impacts of these different pixel value extraction methods or compare to different spatial resolutions of remotely sensed imagery. And again, there's just a very, very strong lack of information about CBI more than 1 to 2 years following a fire. Finally, I just want to show this table that was an outcome of this work, which is kind of highlighting these characteristics I've been talking about: spatial alignment, georeferencing inaccuracies, and temporal alignment. What those are, what they mean in terms of field data, remotely sensed data, how they might impact model results, and how a study design might go about trying to mitigate those impacts. All right, so bear with me, chapter 3. Really, this is where the rubber hits the road on this sensitivity analysis and how impactful are all of these decisions in interpreting how a fire is occurring on the landscape. So how much difference would it make which method you actually use to model CBI? Can these methodological decisions be ranked relative to their influence on model results? And I was really curious about accuracy and precision here. And then how might the interpretation of a fire change depending on that model selection? So this work went on at the King Fire, which occurred in 2014. We can see that it was disproportionately high severity. It's made a strong run, I think, front 100,000 acre landscape in an afternoon. There were 50 remote CBI plots scattered throughout the fire area. And then we placed 3 quote unquote pseudo unburned field plots, which means they weren't measured on the ground, but I used remotely sensed data, aerial imagery to randomly place plots outside the fire perimeter and check that they had not been disturbed between pre and post fire. And those can be used to anchor regressions at the low end of the range of severity. So as we look at this, we see across the top CBI plots, and then this second row is the panel of geo-CBI. And then the columns here are overall plot severity, understory, and overstory. Overall, that is just proportionally high number of plots at higher levels of severity. So severity is along the x-axis here. And we also see kind of this decoupled fire where the understory tended to burn at very high severities, whereas the overstory was a little bit more even in its distribution across severity levels. Here's all of the metrics we threw into this sensitivity analysis. I don't want to really go through all of them in depth, but the type of the field plot, we had two options. We modeled across three combinations of strata: overall, understory, and overstory. Whether or not those pseudo unburned plots were included in the analysis, two different sources of imagery, 7 different pixel values where they're all based on NBR, and whether or not they included that offset value, 8 different sampling options for extracting that pixel value and associating with the plot itself. And then that created 1,344 combinations of predictor and response variables that we ran 11 different models for. And so this is kind of the visual of that occurring, where each one of these is a different model itself, a different set of predictors and responses, and then all of the models that were run across those. So how do we go about doing this? Here's a pre and post fire red, green, blue imagery. But remember, we're really interested in this near infrared and shortwave infrared bands. And so when we look at this, so this is just really quickly, blue, green, red, near infrared, shortwave infrared, 1, and then there's a second shortwave infrared band. And if you look at this as mapped pre-fire and post-fire, and you can squint to see differences along the top row, but it's really the bottom where you see major differences in reflectance from pre to post fire. And again, this is no surprise to us. Near infrared and shortwave infrared have been shown for a long time to be very sensitive to these effects of fire. And if we plot these with severity or field measured severity on the x-axis, we can start to get a sense of how pre-fire is changing relative to post-fire. So in these plots for each of these bands, pre-fire is the open circle and post-fire is the closed circle. And just as you noticed in those maps, it's a lot harder to distinguish the open circles from the closed circles in the above row than it is in the bottom row. And if we plot just the difference between pre minus post-fire, we see that these are the two bands that go into the normalized burn ratio, near infrared and shortwave infrared 2. We see that they show very strong monotronic trends with increasing severity. Near infrared is increasing after a fire, or sorry, it's decreasing, but the difference is increasing after a fire. And the difference in the shortwave infrared bands are decreasing after a fire. And so here's the indices that we're using in this analysis. Again, just calling attention to the normalized burn ratio being based on near infrared and shortwave infrared. And that's actually going into all of these other calculations as well. The only difference is NBR is just using a single post-fire image, whereas either using pre minus post or relativizing pre minus post divided by pre-fire NBR. And so now we're able to kind of picture this fire not in the red, green, blue space, but in a index space, a spectral index scale. And so here's pre-fire NBR and post-fire NBR, and we're really starting to work with these data now. We had two different sources for our imagery. One is done by scene selection, and one is a composite image. And we use these 8 different methods of pixel value extraction to associate the spectral index with a plot. 11 different models were run, and these were all ones from chapter 1 that we found appeared in the literature. And again, I just want to highlight the breadth of work that was done here. So getting into the results, what do we find? This panel shows for each decision in the, this is inclusion of unburned pseudo plots and data source. Each decision, the different options that you could make within that decision space, and then the marginal distributions of root mean square error for each of those decisions. So one thing to remember here is that the CBI scale, and I didn't mention this, but it goes from 0 to 3, where 0 is unburned and 3 is severely burned. And so these RMSE errors range up to about 0.5. And this indicates to us just generally about a 10 to 20% model error is occurring. But the key takeaway from this kind of image is that, hey, you don't see big differences, right? That means that there's really no one overwhelming decision option that's overriding the accuracy of these models. What you do notice is that some of these distributions have long tails and some do not. And that suggests that there is compounding error throughout this process, which means that, hey, most of the time, you're going to end up pretty similar, regardless of what other decisions were made, but you can go very wrong. If you make the wrong decision at every option on this chart, then you can end up with a relatively poor performing model. And so we took all of those options and plotted them relative to one another and looked at, this is my chart of accuracy on the x-axis versus sensitivity on the y-axis. So mean root mean square error and the coefficient of root mean square error. And what that means is if you have a low root mean square error, you're generally producing accurate models. And if you have a low coefficient of variation, that means you're not very sensitive to the other decisions that are occurring throughout the analytical process. And so overall, we would categorize good decisions generally as being ones that produce accurate models and are less sensitive to the other selections in the modeling framework or the other steps in the analysis. And then yellow means you're accurate or sensitive, but not both. And red is you're neither accurate nor sensitive. Each of these quadrants is plotted relative to the data that's included in them. And so I just am going to highlight here that these two being close together is just a matter of me placing the axes and doesn't mean anything different than these two being far apart, but it's really kind of the space of quadrant that you fall in that I want to highlight. And this does show us that there are generally some things that I think are producing relatively accurate models. And by being less sensitive or more precise means I think that those metrics may be more comparable across different studies that may have used different methods to produce their models, right? Because if they're less sensitive to those modeling workflow choices, then it means that you probably came out with a similar result, and we could probably compare those better and like compare those in the sense of understanding the ecological phenomena without being as worried that the modeling framework is driving those differences. And so getting to, this is just nearing the end here. This is the quote unquote best models if we just consider model fit, the root mean square error. So remember I brought up this concept of, hey, what do things look like if we just uncritically pick a model using a performance metric like root mean square error? How might that juxtapose against selecting a model and an analysis pathway that's more in tune with the ecological things we're trying to model or assess? So what I'm going to put that into a little bit more layman terms here is what's happening here. Some of these models, these are cubic or quadratic model, is actually predicting a reduction in severity, so y-axis being severity, a reduction in severity at very high values of this spectral index. In this case, it's RD and BR, and that's not expected. It's kind of overfitting the data, and it means that we can't distinguish areas that potentially we probably, based on the spectral index value, are very high severity, but are being categorized the same as areas that have slightly lower values of that spectral index. So that can be problematic because it means that we can't distinguish on the high end of the severity spectrum some of these areas that may be important for management considerations. Also, we see some of these models intersect axis at above zero, and that means that we're not predicting anywhere within the modeling environment areas that have burned or very low severity. And I know there's areas there because I placed those pseudo unburned plots and I buffered the fire perimeter by 300 meters. And so I know there's areas that are unburned. that these models would not be capturing. And there's also models that go to negative infinity or produce negative values of severity, which is outside of that 0 to 3 scale. Maybe that's less important. We could reclassify those to 0, but it's still not behaving how we would expect these to occur in the real world. So I went through and said, hey, this will take just a moment to explain. This first set of panels is the best model, quote unquote, best model for overall severity, overall GeoCBI, understory GeoCBI, and overstory GeoCBI. And then the second column, I've plotted the simplest model, a linear model across of these data. And then the third, I plotted Gompertz model. And I picked Gompertz just because it tended to reflect what I thought, avoid some of those pathologies of the other models, in the sense that it does predict areas of low or no severity, and it doesn't result in reductions in severity at very high values of the spectral index. And so what you can see here is that the trade-off between these models, going from, oh, sorry, this is a bad example, the overstory, because this best one was the Gompertz one. So if we look at the understory, the quote unquote best one had a root mean square error of 0.271. So that was best just based on root mean square error, which is lower than the Gompertz one. And similarly in the overall severity. So maybe what the suggestion here is you're accepting a little bit more error or inaccuracy in the model itself in order to achieve results that more accurately reflect the expectation of the environment and the behavior of the sensor and the system itself. What does that mean? Well, some of these areas of low to no severity, those could be areas that provide seed source for future forest regeneration. And so maybe you don't need to plant around those areas. These models are able to capture that. And then if we just classify those data and kind of interpret them relative to those distributions of severity, we see that in some cases, a Gompertz model, this is Gompertz versus in the light gray versus a cubic, or the best model versus RSME. Gompertz is predicting more high severity areas, and it's also predicting more low severity areas in the overall GeoCBI. And so I don't want to go through all of these right now, but I want to highlight that it does in fact the fire across the landscape. And what I haven't gotten to yet is what I think a good next step for this type of work would be is to map these spatially. Because say, okay, we're able to capture those very low to none burned areas. Are those actually occurring interspersed without the, like throughout the fire, or are they just within the perimeter itself? Because ideally, from a management standpoint, it's more important if they're interspersed throughout the fire itself, and they could serve as seed sources. So just as an example, how inferring results aspatially like this provides some context to what's going on with these models, but there's another context that we're potentially missing that could be added on with the spatial configuration analysis. So the key takeaways here: no single decision is really having an overwhelming impact. These options do vary in their relative accuracy and precision, and we're able to kind of map and diagram that. The error can compound through the analysis if you make the wrong decision every step of the way. And we haven't done that. That would be a very, very in-depth job that I don't think I'm quite ready for, given the number of different models and options we've run. But it is possible, if you did everything wrong, to end up with a relatively poor model, and that the selection influences the fire interpretation. What I think that does, from a key like high level takeaway, is that generally these models don't behave very, very poorly relative to one another. There are some pathologies that introduced But I think that we can focus a little bit more on interpreting the ecological consequences than being hyper focused on all of these methodological choices and trying to wring out more and more R squared values out of the data right now. So overall synthesis, there's a lot of ways to predict CBI. There's no best model. The recommendation here is don't pick uncritically just based on a performance metric. Consider the ecological application, and then report the reasonings that you're making these decisions, and consider, again, consider the application of your assessment. And I think as long as you don't choose wrong at every step, we can generally say, based on this one analysis, so this needs to be redone on multiple fires and across different ecoregions, but this suggests that results may generally be more comparable than the different methods might kind of suggest. Okay, I'd be remiss if I didn't include this slide that just from this paper that's really arguing that we need to measure direct ecosystem phenomena and relate them with remotely sensed data, and we're losing too much by aggregating things through the composite metric. While I do agree with that on one hand, when we don't have very targeted applications outright from the outset of how that severity metric will be interpreted, I do think this kind of general CBI approach is still valuable. And then I think that I'm just going to move to questions, but there's a lot of next steps where this could go. And I'm sorry for the people that came here to see a LiDAR analysis. We did some work. There just were too few plots that were covered by pre and post fire, and they were very high severity. So results were somewhat promising, but just not enough data to assess a full chapter with. Thank you all for hanging in there with me. I know that I should have slimmed that down more looking at the time now. So much thanks to my committee. They've been patient and supportive and provided invaluable mentorship across this whole process. So thank each and every one of you. All of the funding people and people that I worked with on projects not directly related to this work, or whose funding helped support these projects, and then the school for the TA and instructor support. Harry, man, like all of the conversations we've had about modeling and uncertainty and robustness, and all of your buzzwords and help over the past few weeks, totally invaluable. There's a ton of people in Rascal and PFC that I would like to thank. I just listed the ones here who really directly contributed to this dissertation itself, but definitely not meaning to leave others off the list. Just way too much people have helped me along the way. And then my friends and family, of course, my parents and my partner, Emmy, and again, just everyone else along the way. And my current employer, Vibrant Planet, has been very patient and flexible and allowed me to finish while I've still been working with them full time. So thanks to them.